section 3.5, for this next test, we're going to learn about one more set of derivative rules. So this lesson not as conceptual, it's more rule-based. Of course, we want to understand where the rules come. A couple identities to have in your mind as you go through this lesson are your reciprocal identities. So secant of x is 1 over cosine of x, cosecant of x is 1 over sine of x, and so on. And then you also have your Pythagorean identities. We talked about how to derive those and where those are earlier in the semester. So we're going to focus on the rules. I'll say a brief word about where they come from. And again, none of these are provided, so you will need to make sure you know them for the tests. So the derivative of sine and cosine can be derived from the limit definition of the derivative using various identities and limit properties. You can see the e-text if you are curious about the exact derivation. So if you were to go through that, you'll end up with the derivative of sine of x being cosine of x. And again, this right here is the rule. The derivative of sine of x is cosine of x. To get this, kind of maybe just say, like, all we're really doing here is finding the limit as h approaches 0 of cosine of x plus h minus cosine of x divided by h. In order to go ahead and do things like this, it's not too bad. You would just have to use like your addition formula, and you would just have to break up the limit using various properties of limits that we worked about in chapter 2. So it's really reasonable, but again, just the main focus on this lesson is the rules. If you would like to go ahead and actually see the derivation from this to this, you could go ahead and consider the e-text. So with that rule, let's go ahead and consider a few different scenarios with the context of the other rules. So number one is just using the sum and difference rule and the power rule with this new rule. So y prime, the derivative of the given function, is, well, 2x, nothing new with that. Then we have minus the derivative of sine of x, which is cosine of x. So there is the very simple version of the problem, where it's just used with a power rule and the difference rule for derivatives. Number two, let me just kind of make a quick caution on this one. So the caution is, you might say y prime is equal to e to the x times cosine of x, which seems really simple, but is that correct? This right here is the common mistake. That is wrong. What rule did we neglect to use here? Product rule. So remember that if you have a product of two functions, in this case we have e to the x times sine of the x, you do need to use the product rule. So I'm going to just box this off to the side as a little bit of caution. The actual derivative, y prime, let me do it down here so there's room, is first times the derivative of the second, which is cosine of x, plus the second times the derivative of the first. Be very careful to make sure that you actually put a multiplication symbol there, because if you didn't, just as a side note, if you didn't, you would assume that these are grouped together. So more common, if you're going to use the product rule, be careful with that. Typically, we'll write the e to the x first. So typically, you'll see e to the x cosine of x plus e to the x times sine of x. So that is that's the more common way to write that equation. Or if you're just feeling like some factoring, you can just go ahead and pull the e to the x out and be left with e to the x times cosine of x plus sine of x. Just if you felt like spitting some facts or something. Some facts. Okay, factoring. There's a stretch. Oh, hey, is that the Pythagorean identity? No. So these are not squared. So remember, this right here is your derivative. That is not the Pythagorean identity. You do need to have the squares to go ahead and change that to 1. So any of those forms are fine. Just make sure you realize they're all equivalent. But does anyone have any questions on number 2? All right. So let's move along, and in number 3, we're going to go ahead and get the derivative of cosecant of x. we can go, we're going to derive it once, but again, it's one of those things you'll want to have commit to memory, so you don't have to go through the quotient rule every time you need to take the derivative of this one. But remember that a little bit of algebra first will give us that y is equal to 1 over sine of x. And then we just use our quotient rule. Low d high minus high d low over low squared, don't you know? I always change the end to that little rhyme, but I just remember start low. So, y prime, let me change color here. The derivative of y is going to be sine of x. I'm going to go ahead and show my work here, times the derivative of the top. So I'm going to just kind of not take the derivative here. I'm going to just kind of show the rule. So start low, derivative of high, so low d high, minus high times the derivative of the low. So I'm going to just use this prime notation right here. And then all divided by sine of x all squared. So I haven't taken the derivative yet. I've just applied the quotient rule. So now let's take the derivative in the ones that are in red. So this will be sine of x. And then what is the derivative of 1? 0. Remember, the derivative of a constant is 0. So this will be 0. So that little 1 prime is the derivative of 1. Minus 1 times the derivative of sine. And again, what is the derivative of sine? Cosine. That's correct. And then in the denominator, I'm going to just leave this as sine of x still squared. Remember, you could have also chose to write this as sine squared of x if you wanted, but I'm going to show you why I didn't do that here in a moment. So that step, I just took the derivatives as I specified in red. We have some cleaning up we can do. So y prime here is going to be 0 minus, so it's just going to be minus cosine of x divided by sine of x, still squared. But what I'm going to go ahead and do, let me write it like this because, slide that over. Let's look at what I have right here. I'm going to go ahead and break up that sine of x squared in the bottom to this. Does everyone agree that what I've written here is equivalent to the what's above? The 0, let me just maybe note this, the 0 crossed out that term. And then we had 2 sine of x's on the bottom, so I just simply separated the fractions. The reason I did that is because it's simpler to go ahead and write it back in terms of the initial identities. So what do we have right here? We have y prime is equal to cosecant of x times a minus cotangent of x. But I'm going to go ahead and just move that minus sign to the front since it's all multiplication. So right here is the simplified expression. So maybe more commonly, just to kind of put this all together, the derivative of cosecant of x is minus cosecant of x times cotangent of x. So this right here is another rule for the derivatives. So we now know about sine and cosecant. Let me see. Anything else I wanted to say on that one? Nope, not yet. All right, so all right. Any questions on number 3? So again, I'd recommend memorizing that rule instead of having to go through the derivation each time. But of course, if you forget, you could go ahead and work through the quotient rule without much difficulty. It's a little long-winded, but not too bad. All right, so I'm going to go ahead and help you make connections about like what are the rules once we have them all. So let's go ahead and look at the next page. The derivative of cosine we actually looked at earlier in the course when we were, I think, in section 3.2. The derivative of the cosine function is the negative of the sine function. And you can see that just doing some basic ideas as before is remember whenever you have your max and mins, your horizontal tangents, when you consider the graph of the derivative, these are your x-intercepts on the graph of the derivative. And then just the other ideas we talked about before, wherever the graph is decreasing, that is where you're going to be in a negative quadrant in the graph of the derivative. So this is really more of a construction by the graph, and you can see what we end up here with is this is minus sine of x down here. So y prime, the derivative of cosine is minus sine of x. Again, you can derive this using the limit of the difference quotient if you want, but you won't need to use the limit of the difference quotient on the next test. You can just use them by the rules that we've set up. All right, so we have a series of examples right here to kind of look at it in the context of our other rules. In the case of number 4, we have the derivative of 5 e to the x plus cosine of x. Well, this first one is simple because the constant multiple rule and times the derivative of e to the x is e to the x. And the derivative of cosine, be careful, is going to be minus sine of x. So do be careful because notice because this was plus, this becomes minus. Suppose we had another exercise like 4b where it was y equal to 5 e to the x minus cosine of x. This is the scenario where its derivative would then switch back to positive sine of x. So just be careful with your signs that because if there was another minus there, then you would have to go ahead and apply the double negative to make it positive. So fairly basic one, but not too bad. So any questions on number 4 or 4b? Okay. Number 5, again, make sure you use the product rule right here. So now that we have sine and cosine in play, you could go ahead and use the product rule here. So let me give you a moment to just try this one. So remember to use the product rule just to see if the ideas have set in your mind and give you a moment to process. So what we'll find right here is y prime is equal to sine of x times minus sine of x, the derivative of cosine, plus cosine of x times sine of x, which is going to be cosine of x. So y prime, the derivative, is going to be minus sine squared of x plus cosine squared of x. You may have also decided to kind of put this first, the cosine squared of first, so you may have done minus cosine of squared of x, or excuse me, positive cosine squared of x minus sine squared of x. Either of these are okay, and you might be thinking, oh look, I got my squares. Is this the Pythagorean identity? Remember the Pythagorean theorem is the sum of the squares of the sides is equal to the square of the hypotenuse. So the fact that this is a difference means that this is not the Pythagorean identity. So either one of those are fine. You could go ahead and do some other things with like the half angle formula and other identities, but this is as good, as clean as she might be for now. Yeah, you could do some other stuff if you wanted, but this is fine. Any questions on number 5? Anyone get it before me? A good amount of you. Awesome. Just want to give everyone a moment to process. So down here in 6 and 7, we're going to go ahead and learn our rules for secant and tangent. So again, once we derived them once, I do that to show you where they come from. But you're welcome to memorize them and kind of shortcut your way to the derivatives with this. So again, the first step here is just to go ahead and write secant in terms of its not cosecant, in terms of its reciprocal, so it's going to be 1 over cosine of x. And then this one's going to play out very similar to the one we did number 3 earlier. So it's going to be low, so cosine of x, times the derivative of high. This time I'm going to just take the derivative of 1 to get 0. Then remember that it's not plus, but it's minus, so low d high minus high, times the derivative of cosine is going to be minus sine of x. And then all of this is going to be divided by cosine of x all squared, or cosine squared of x if you chose to write it that way. So that's just a quick application of the quotient rule. So clean this up now. You end up with sine of x in the numerator because, again, the cancellation of the cosine of x with the 0. And then notice the double negative here is why it's going to be, when you're multiplying that, that's why it becomes positive. And then you would still have the cosine of x all squared in the denominator. Of course, we'll want to rewrite this using the simpler functions instead of as a quotient. We'll rewrite this as 1 over cosine of x times sine of x over cosine of x. So you can see right here we have y prime is equal to secant of x times tangent of x. So maybe just to put the rule stated simply at the bottom, the derivative of secant of x is equal to secant of x times tangent of x. So if you take a sec to get the derivative of secant, you'll also end up with a tan. Get it? Because you'll also end up with a tan, secant, tangent. Okay. It's those things that help me kind of remember those in the context of not having to drive it. Notice also that there's also that pattern that when you considered cosecant, it was cosecant, cotangent. So when it's secant, tangent. And remember that the derivative of cosecant also had the negative. So any questions on this one right here? All right. Number 7, again, is tangent, but we can derive this similarly just using the quotient rule, recalling that the tangent is sine of x over cosine of x. So not too much new right here. I think you may be able to do it independently. So let me go ahead and give you a moment just to get your hands on it and see if you could apply the quotient rule to go ahead and find the derivative of tangent. But notice, finally, in this one, we finally do have the Pythagorean identity. I've been looking for it all day. So, Pythagorean identity. So that is how we go from this step that I've highlighted in blue to the one down here below. But overall, you don't need to go through this derivation every time. I won't do it in the future should I need to take the derivative of tangent. But if you're looking for a tangent, it's going to take you 2 seconds. So secant squared. Yes, Savannah.
Why did you set the numerator to 1 instead of canceling the cosine squared?
So remember that if you were to go ahead and consider this in terms of like division, you're looking at canceling this, but remember that whatever you divide by everything in the numerator must be divided by it. So it's not as simple as just crossing that out. What the work would actually be, maybe let me do it off to the side just for reference. You would have to do cosine squared of x over cosine squared of x plus sine squared of x over cosine squared of x. And if you continue this thought process, you would have 1 plus tangent squared of x, which is still secant squared of x. So notice again, this would just be another form of the Pythagorean identity right there. So that's the thing to watch out for. When you cancel, you don't get rid of them, it reduces to 1. And if you are going to divide, you do have to divide each thing in the numerator by the denominator. So maybe just a little bit of a fraction rule that you may just want to practice with and remind yourself a few times. So we now have the derivative of the tangent. Is secant squared. Any questions on that one? Any further questions? So again, we could actually go through a similar differentiation process for cotangent, but I'll just go ahead and state it on the next page. So let's summarize the rules. The derivative of cosine of x, or excuse me, let's do the sine of x first. The derivative of sine of x is cosine of x. The derivative of secant is going to be secant of x times tangent of x. Because if you need a sec, you'll get another sec, and you'll also get a tan while you wait. Tangent of x is, its derivative is secant squared of x. Notice that tangent and secant are going to like to hang out. So you can see like secant of x is secant of x, tangent of x, but tangent of x, to get a tan, is going to take you 2 secs, so secant squared. So the derivative. Cosine is going to be a minus sine of x. So you can see that cosine and sine kind of have this switching idea. But just remember, when you take the derivative of cosine, it is negative sine of x. The derivative of cosecant of x is going to be minus cosecant of x times cotangent of x. Notice the similarities between secant and cosecant. And notice that c's like to hang out. So notice here that the c's like to hang out. And then the other thing, cotangent, we didn't derive it, but a similar process will end us up with minus cosecant squared of x. Again, noticing that c's like to hang out. And while I know that you guys all think calculus is your favorite course this semester, it does take quite a bit of time, which is sometimes a negative. So something, if you notice, all of the derivatives that start with c end up with a negative. So just some patterns will help you. I know calculus is your favorite, but take some time. So there's a negative to it. So there's the negatives that start with c. Y'all can laugh in your heart. It's okay. You don't need to laugh out loud. So these are the your 6 derivatives for the 6 standard trigonometric functions. Does anyone have any questions on those? Okay, so just to do a couple other examples together, I'm going to make some recommendations. Notice here it says use the trigonometric identities to simplify and then find the derivative with respect to x. So again, my recommendation is a little bit of algebra is going to save you a lot of bit of headache. A lot of it, anyway. So as you look at these, always think about, can I do quick little simplification to save me some, maybe some steps later? In this first one, notice that you can distribute the secant. So if you do that, I'm going to go ahead and do 2 steps at the same time. We're going to end up with sine of x, but remember that secant of x is 1 over cosine of x. So I'm going to do 2 things. I'm going to distribute, but I'm also going to use the quotient. Well, I guess this would be I should say it's the reciprocal identity. So secant is 1 over cosine, and when I distribute this, notice that we end up with y is equal to tangent of x plus 1. So that quick little step, I no longer have to worry about the product rule. And I don't have to remember sine, cosine, and secant's derivative. I just have to figure out, well, what is the derivative of tangent of x? What is it? Secant squared. And the derivative of 1 is 0. So y prime here is simply secant squared of x plus 0, which I won't write. Oh, I'll write it. Why not? So a quick little moment to think about the identities and the simplification, just using some algebraic properties will save you, really makes a hard calculus problem into an average algebra problem, or should I say a mediocre average problem based off our conversations from earlier. But definitely not maniacal by any means. If we look at number 9, this looks quite morbid, but instead of using the quotient rule, remember that you can rewrite this as 4 times secant of x plus cotangent of x. So if I'm giving you that, take a moment. What do you think is the derivative? Let me give you a moment to think about it. Recall. Try to hide the top of the page so you can't just look at the rules. Hopefully you said 4 secant of x times tangent of x. But when we consider cosecant squared, what are we going to have for the sign for the second one? Negative, because the derivative of cotangent indeed is minus cosecant squared. Okay, so not bad. Any questions on 8 or 9? Yeah, Destiny?
I think I got my math wrong. 'Cause
With what?
the number 8.
Sure,
Sorry, I was gonna ask about it.
no problem.
So I understand the process of how we got from sine of x plus cosine of x to secant squared x, but where, I didn't realize that secant squared of x was applied to the problems inside the first part. My mistake.
Okay, we're good. It clicked. Great,
Sorry.
no problem. Okay, let's take a look at numbers 10 and 11 right now. So again, you could use the product rule, but, oh man, this one is maniacal. Maybe a little bit morbid, but you'll see at the end. So again, a quick little bit of algebra first will give you a secant squared of x plus, let's see, outside is going to actually be minus secant of x times tangent of x. And again, you may have noticed this is a difference of squares, so those inner terms are going to cancel. So we would have plus secant of x times tangent of x. Ooh, this is a long one. Let me slide that over. And then we finally have minus tangent squared of x. So there's a lot of terms right there. If you notice this as a difference of squares, that would be helpful because then you would just recognize that those would cancel immediately. So what we end up with is y, not y prime. This is still the original function. We haven't taken the derivative. Is secant squared of x minus tangent squared of x. And really at this point, we would still need the product rule because we haven't talked about the chain rule, the one rule that will allow us to work with composite functions. So hopefully at this point, you're looking and be like, this looks like it could be easier. And I'd be like, you're right. And you'd be like, right, Pythagorean theorem. Because this is just 1. Remember that cosine squared of x plus sine squared of x is equal to 1, but secant squared of x minus tangent squared of x is also equal to 1. It's just a rederivation or a reformulation, I guess I could say, of this one where the tangent was moved over. So secant squared of x minus tangent squared of x is equal to 1. And, well, I told you this was a little maniacal because that looks nasty, but what is the derivative of 1? 0. Okay, cool. Just little things to watch out for. You'll notice as you do more problems involving trig, you'll recognize these little moves. And then in number 11, this is also similar to the idea you asked about earlier, Savannah. So remember that when you divide, you do sine of x divided by cosine of x plus cosine of x divided by cosine of x. That each thing in the numerator is divided by whatever is in the denominator. So we end up with y is equal to tangent of x plus 1. So we end up with y prime is just equal to secant squared. Yep, 2 seconds to get that. Okay. So does anyone have any questions on 10 or 11? Okay, so let's see what else we have. Oh yeah, 12 and 13. I think 12 is a problem you encounter in your homework. So we'll go ahead and do a quick little walkthrough of it right now, just so you have something for reference. Has anyone encountered this one in the homework? Does it have a view and example or not? Do you know?
I don't know, there's like 3 of them.
So there's a couple of tough ones.
The first one was very simple.
Awesome. So I can't remember if this one has a view and example in the homework. So we'll walk through it just so you have a worked out solution, so you've had a chance to reason through it. But you'll encounter something like this in your homework. All right, let's go ahead and read through it first. Find all points on the curve y equal to cotangent of x with the restriction that we're only going to be considering the x values between 0 and pi, where the tangent line is parallel to the line y equal to minus x. We're then asked to sketch the curve and tangents together, labeling each with its equation. Wow, this is a very demanding problem. But that's okay. It puts a lot of ideas together. So our function that we're working with is y is equal to cotangent of x. So notice that this is the one I'm going to want to take the derivative of, because this is the one where I'm asked to go ahead and find the points where there's tangent lines. So basically, I want tangent lines on this curve, so I'm going to need to take the derivative of this one. So that is to say, its derivative is just going to be y prime is minus cosecant squared of x. I don't need the derivative of y equal to minus x because I don't need to find any tangents on that curve. I'm just asked to find the tangents on the curve y equal to cotangent of x. Okay, so that's kind of a little bit. So it asks us to find all points where the tangent line is parallel to this line y equal to minus x. So notice what I'm given here is that y prime is equal to minus 1. Where am I getting minus 1? Notice that this right here is giving me the slope of the tangent line. It is negative x, so the slope is just minus 1. So what that means I need to do is solve minus cosecant squared of x equal to minus 1. Okay, so cosecant squared of x is equal to 1 if I multiply both sides by the negative. There's a couple approaches you could take to this one. Let me think about this for a sec. I prefer to think about solving in terms of sine and cosine because I could quickly just reference the unit circle's x and y coordinates. So my suggestion right here, let's see, if I take the square root now, I could do that. So I'm going to go ahead and take the square root now. So we'll have cosecant of x equal to plus or minus 1. All I'm doing is taking the square root of both sides. Remember, when you take the square root, when solving, you do need to consider plus and or minus. However you get here is really fine. So this is 1 over sine of x is equal to plus or minus 1. If you cross multiply or reciprocate, ultimately we end up with sine of x is equal to plus or minus 1. Everyone good so far? I'm not quite solved yet, but I'm at a point where I can think about the inverse right here. I'm not really taking the inverse of both sides because they told me my restriction is actually the same restriction as the arc sine function. So, well, not really. So, but keep this in mind, 0 to pi. If we think about solving this right here, we end up with x equal to, okay, here's the thought process. We have two x values. Let me draw a unit circle. Or not, we're going to find two x values. On the unit circle, where are the y values equal to plus or minus 1? Right up here. Why the y values? Because we're looking at sine. This is the point 0, 1. This is the point 0, minus 1. So what we could see right here is that the x values are pi over 2 and 3 pi over 2. If we're considering the first time around the unit circle. But remember, up at the top, it told us what? We want the solutions that are between 0 and pi. So I can go ahead and discard which one of those? I can discard that one because the only part that it cared about was the ones between 0 and pi as your angle. So we have the x value. So the point. So we're almost to our answer. in terms of find all points. There's only one. To find the point, we need the associated y value, which we get by just doing y equal to cotangent of pi over 2, which is, it's just going to be 0. You could think about it. I'll do the steps in my mind, or that I would be thinking in my mind. Cosine of pi over 2 over sine of pi over 2 if you're using the quotient identity. So you get just 0 over 1 or 0. So the answer, the point, would be pi over 2, comma 0. So that's the point of tangency. That answers the first part of the question. Is everyone okay so far? Anyone need me to recap anything? Take a moment, process. Take a sip of water. I forgot my water bottle at home today, and I'm always nervous when I don't have something with a lid, because my first year of teaching, I had a big Nalgene that didn't have a lid or anything on it. So like middle of class, I've knocked over a whole bottle of Nalgene. It's like the big 64 ounce ones or 32 ounce. Yeah, it was embarrassing. But I was like, let's just do the math. All right, just sharing nice stories. Okay, so the second part of the question, sketch the curve and the tangents together, labeling each with its equation. So just to maybe have a quick little sketch of cotangent. I'm going to actually just sketch it in the first quadrant because it just wanted it between 0 and pi. Remember that there is a asymptote through pi. And the graph of cotangent is going to go right here through pi over 2. Cotangent is a decreasing function going through pi over 2 with asymptotes at multiples of pi. The tangent, though, to get the equation, what you need to do is just do y minus 0 is equal to minus 1 times x minus pi over 2. So we end up with y is equal to minus x plus pi over 2. So if you kind of wanted the actual equation, this is not scaled very well, but you would have the tangent line going something like this. There. So you can see in green is the associated tangent line. So a little bit off my scale, but it gives you the general idea. And I think on the homework it would be a multiple choice. Select the one that correctly describes the situation, so forth. Okay. Any questions on number 12? So hopefully that serves as an example to help you reason through it. 13 is just a matter of pattern matching. So this is just kind of, I'm going to give you a tip on this. Take a bunch of higher order derivatives. So basically just keep taking the derivative. Take a bunch of higher order derivatives until it repeats. We did something very similar with e to the minus x. Basically, the pattern was it just took 2 until it started repeating. So I'm going to leave that one as a little bit of a challenge exercise. Take 4 to 6 derivatives until you start noticing the pattern.